Hey everybody, welcome back to chemistry. And so what we're going to talk about this time is I want to explain what state symbols are and how they are added into chemical equations. And then what I want to do is sort of briefly go over the three general types of chemical equations that we're kind of covering in chapter 4. One type is called an ionic reaction, one type is called an acid-base reaction, and one's called a redox reaction. But really we're going to need some preliminary information to really understand some ionic reactions. And so one thing that we need to go over is I sort of need to explain what dissociation is. That's a very important concept in ionic reactions. And then I need to sort of explain what precipitation is. And then I need to talk about the solubility rules for compounds. And so that's a fair amount of work. And then the last thing I think I'm going to go over is to try to explain what electrolytes are. And all these are covered in sections 4.1, 4.3, and 4.4 in your book. Okay, so a lot of times you will have chemical equations, and then you'll have to include something called state symbols. So what I'm going to do is try to explain this to you sort of in the context of actual chemical equations. And so what's going to be a little bit different this time is before what we did is we took a look at equations that have formulas and we just kind of balanced such that the atoms for each element were balanced on either side of the equation. But now what I want to do is I want to start out with a word equation and then convert that into a chemical equation and then balance that and then include state symbols. So let's go ahead and try the first one. So the first one is aluminum metal is added to an aqueous solution of hydrochloric acid, producing the products aluminum chloride and hydrogen gas. Okay, so before we launch into that, let me sort of mention what the four state symbols we usually use in chemistry are. So one of them is parentheses S. And so if that's beside a compound, as you'll see in a few minutes, that indicates that the compound is in the solid state. And then if you have an L here, then the compound or element is in the liquid state. And if you have a G here, it's in the gaseous state. And then there's one you may have heard of, or maybe not, but it's AQ. So AQ stands for aqua, which means water. And so this refers to an aqueous state. So let me talk a little bit about what that is. Okay, aqueous state usually refers to a situation where you have compounds, oftentimes ionic compounds, dissolved in water. So if you have a case where you have an ionic compound, you kind of can tell from the explanation of the problem that the ionic compound is dissolved in water. What you would do is, if the ions are dissolved in the water, we'll talk more how you figure about that later, but if the ions are truly dissolved in the water, you indicate that by using the symbol AQ after you write the formula for the ions. So I think the best thing for me to do is just sort of explain that with a few problems. So let's do the first one. So again, we have that word equation there, and so I'm just going to take that and write a chemical equation. So when I write it, it will not be balanced. And also I want to include state symbols. So we have aluminum metal. So we have Al. And so if it's a metal, you can probably guess it's in the solid state. So we would indicate that by putting a little parentheses S there. And it says it's added to aqueous hydrochloric acid. And so eventually you'll learn the formulas for acids. And so you will learn that hydrochloric acid is HCl. And we have some information about it. It said it's an aqueous solution. So what that indicates is that there's probably some hydrogen chloride dissolved in water. If so, these are ions dissolved in water. And so you would indicate that this compound is dissolved in water by putting an AQ here. And then, so we have these two materials. One is an element, aluminum, one is a compound. And apparently they're going to form products. And so let's see what those are. So we have one product is aluminum chloride. Now, it may be difficult to understand from the question itself what state this is, and so you have to use maybe sometimes a little bit of imagination. And so what you might expect is as this reaction goes, the reactants go away and products form. So what is going on is products form in this aqueous solution. So you might imagine that this ionic compound will form an aqueous solution. So you might make a good guess that this is AQ. But also another product is hydrogen gas. And so hydrogen gas is H2, and then this is G. Okay, so now I gotta balance this guy. Well, we don't want to leave an equation unbalanced here. So I will try to do this kind of as quickly as I can. So what I'm gonna do, just let me put a 2 here. And so we have 2 aluminums. I'll balance that aluminums last because that is an element on this side of the equation. Let's go for the chlorines first. So we have 2 times 3 chlorines is 6 chlorines. So to have 6 chlorines here, I put a 6 in front of here. 6 hydrogens here on the reactant side, 2 hydrogens on the product side. So I'll put a 3 here. So the hydrogens are balanced. And so the last element I'll balance is aluminum, 2 aluminums on the product side, 1 on the reactant side, so that should be a balanced equation. So this is a balanced chemical equation for the information that we have, including state symbols. Okay, so let's move on to the next one. Okay, so in this problem we have sodium hypochlorite salt is added to liquid hydrogen peroxide, which breaks down to produce water, aqueous sodium chloride, and oxygen gas. Okay, so we have sodium hypochlorite salt. So you're going to have to figure out a formula for that. And so it is NaClO. And it looks like it is a salt, so it's indicated immediately that it's in the solid state. So you can write that there if you want. Is added to liquid hydrogen peroxide. I don't think you'd be expected to know the formula for that. I just happen to know that it's H2O2. It's indicated in the problem that it's a liquid state, so I'll put an L here. And then what we're going to do is we're going to get some products. So let me write this down here. We're going to get water as a product. And we're going to get aqueous sodium chloride, so we have NaCl here, and then we have oxygen gas. So let's talk about what states these are in. So water as a product, it looks like we're having other stuff form in the water, so it's not really pure water. There's ions from sodium chloride forming in the water, so water really is aqueous. So we could probably write AQ here. Sodium chloride will be dissolved in the water. Is in an aqueous state, and then oxygen is a gas. So that should be fine. Now, one question you might ask is so if we have sodium chloride dissolving in water and it's in the aqueous state, how about sodium hypochlorite? Why isn't this an aqueous state? And the reason why it's not in an aqueous state is because it's not dissolving in water. Instead, it's dissolving in hydrogen peroxide. And so we cannot really indicate that this is in an aqueous state. So that's the reason. Now, you can balance the equation, but as I recall, things are almost balanced, or it could be completely balanced. So let me check a few things. Sodiums are balanced, chlorines are balanced, hydrogens are balanced. How about oxygens? 3 oxygens in the reactants, 3 oxygens in the product. So it looks like a balanced equation, so that is complete. So that's good. So we will move on. Okay. So let's go on to the next thing. Okay, types of chemical reactions. And so your book talks about 4 types of chemical reactions, and the ones the book talks about are the synthesis reactions, decomposition reactions, single replacement reactions, and double replacement reactions. And in our class, we don't divide reactions generally into those 4 different types, although you could. So instead, we tend to like the types that are described in your book in the driving forces in aqueous solutions section. And so some reactions occur because a major driving force may include the formation of a precipitate. And so if that is the case, it is considered an ionic chemical reaction. But there are other reactions that are included in ionic chemical reactions as well. So it's a pretty broad category of reactions. But if you have one or more ionic compounds in the reaction, then it could be considered an ionic chemical reaction. We'll go into a lot of detail on how you look at those reactions and how you write them out. Talk more about that in a bit. And so another class of chemical reactions are called acid-base chemical reactions. And so we'll talk about that more later. And then a final type of chemical reaction is where you maybe have one reactant actually transferring electrons to another reactant. And when that happens, you may have some rearrangements of the reactants and you get products. But the reaction occurred because the electrons are being transferred from one reagent to another. And so this would be maybe called a redox chemical reaction. So we'll go into some gory detail into what that is. But before we get into these things and before we get into our major topic next time, which is ionic reactions, there's some important basic concepts about ionic reactions I have to explain. So importantly, when you dissolve an ionic compound in water, if it fully dissolves in water, it is said to be soluble. And you need to understand the processes that are occurring for that compound as it dissolves in the water. And this process is generally called dissociation, so I'll explain that right now. So what I want to talk about now is a little bit in more detail what dissociation is. And so let's say you have an ionic salt, and it could be, as an example, sodium chloride. That is an ionic salt, or any other kind of ionic salt, like aluminum fluoride. When you dissolve these salts in water, what is going on is that you are creating solutions of ions. And so this process of taking these ionic compounds and creating solutions of ions is called dissociation. So to understand that a little bit better, I think it's really good to understand sort of what's going on at the molecular level so that we can write chemical equations that represent this process of dissociation. So let's start out with a simple example here. So let's say you have sodium chloride salt at the end of the spoon there, and let's say you're just dropping in the water, and let's say you just add enough so it all dissolves in water. So what you probably will see as it's dissolving is that the crystals basically disappear, and so that reflects what's going on at the molecular level, is that you have individual ions in these crystals being yanked off by water molecules, and they're being separated out, and that process is called dissociation. So let me sort of kind of highlights over what's going on in this picture. So here, maybe on the left side, what we have here is this crystal here of sodium chloride. Now, if you look at the lower portion, we see something kind of interesting going on. You can sort of see here in the lower portion, we have three water molecules ganging up pretty much on the poor defenseless negative chloride ion. So green is the negative chloride ion. And so you can see the waters are ganging up with it, and then they're pulling or forming bonds, weak bonds with the ion, so they can pull that negative ion off. So one little detail to sort of notice in this picture is that we have the hydrogens that are pointing closer to the negative ion than the oxygen. The hydrogens are in white, the oxygen is in red. And there's a specific reason for this, which we'll go into later. You don't need to really understand it now, but the hydrogens sort of have a slight deficiency of charge, and so they're a little bit positively charged. And on the other hand, the oxygen has a slight excess of charge, so it has a bit of a negative charge. And so the water molecules are going to orient their positively charged hydrogens toward the negatively charged chloride ion, and then that will be able to pull off the ion. And then when the ion is pulled off, this is what happens. What you can see is the ion here, the chloride ion, the negative ion is pulled off, and what you'll notice is that now it's surrounded by several water molecules. And again, because the hydrogens have a slight deficiency of charge, they're slightly positive, the hydrogen ends are going to be pointing toward the negatively charged chloride ion, while the oxygens of the waters will be kind of pointing away. Now, the opposite thing happens with sodium. Now, water molecules will gang up on a positive sodium ion, but they're going to point their oxygens toward the sodium. And the reason is because the oxygens have a slight negative charge. And so they'll be drawn to the positive charge of the sodium. And so when you have several water molecules yanking off the sodium will be pulled off the crystal, and then the sodium ion is now surrounded by water molecules, kind of like the chloride ion, but in the case of sodium, the oxygen ends of the water molecules here are kind of pointing very close to the positive charge of sodium. So this will happen over and over and over to all those ions into the crystal until all of the positive and negative ions that are jumbled up in the crystal have been pulled off, and they're all surrounded by water molecules. When that happens, then it's said that the sodium chloride is fully dissolved. And so this process is called dissociation. And so I've got some notes on it here. And one thing to note is when the ions are completely off into solution or surrounded by water, you would say they're dissociated ions. Now, you will note below how I've represented this process by an equation. And so that is an equation for the dissociation of sodium chloride solid in aqueous solution into dissociated sodium and chloride ions. And so what I want to do next is get some practice writing equations for ionic salts being dissociated in aqueous solution to ions. So we'll do that next. So we'll go to the board here. So let's go over that a little bit. Okay, so let's say you have calcium fluoride. And let's say you dissolve this in water. So first off, the calcium fluoride is a solid salt, and so we can indicate that with a state symbol by putting an S here. Now, you're going to dissolve it in water. Can you write a correct chemical equation to describe the separation of the calcium and the fluoride ions in water? So this would be an equation for the dissociation of calcium fluoride into calcium fluoride ions. So the first thing I want to do is I'm going to make a slight mistake to make a point, but then I'll do it correctly. So some people make this mistake and try not to do this. But here, calcium is fine so far. Now, what a lot of people do is they'll say, oh, okay, so it's F2. So they will write F2. Okay, that is not correct. And so let me explain what the correct answer is. Okay, so what you have to sort of imagine what is going on in this compound is why is it that two fluoride ions are part of a formula unit that includes one ion of calcium? And so one of the things you'll have to remember is that calcium has a 2+ charge. So when the calcium ions are yanked off by the waters and are separated off, now you have calciums that have ion. You can see that we want to represent those ions with a 2+ charge. So we indicate the charge in the elemental symbol. And then we indicate that the calcium is now surrounded by waters by writing a state symbol for the calcium ions, which is AQ. Now, going back to the formula unit, you might remember when we're taking a name of a compound, we're writing a formula, we need to balance charges. And so we took two fluoride ions, each with a negative charge, to balance a single calcium ion with a 2+ charge. And so here what we have to write in the dissociation is the fact that each formula unit is really you have two fluoride ions stuck to the calcium, but then when it drops into the water, the calcium separates and the two fluoride ions separate from themselves, each with a single negative charge. And so we have to indicate that. So to do that, what we do is we indicate we have fluoride ions, each has a negative charge, and we have to balance this and show that the two fluoride ions separate from each of these calciums. So we put a 2 here, and then we write an AQ here to indicate that these ions are dissociated into the water. Okay, so there's that one. Let's move on to the next one. Okay, how about barium hydroxide? Okay, so if you had barium hydroxide salt and you were to dissolve that in the water, can you write a chemical equation that describes its dissociation? So let's go ahead and do that. So you have barium hydroxide, and so we have to include a state symbol in the dissociation equation. If it is a salt, it is a solid, so we will put a parentheses S here. And then when we add the salt to water, you get the barium ion dissociating from the two hydroxide ions. So you have to remind yourself, the reason why two hydroxides bind to barium, each hydroxide with a single negative charge, is because a single barium ion has a 2+ charge. We have to indicate that in the dissociation equation. So we write Ba2+, and to show that it's dissolved in water, we write aqueous. Okay, and then here the hydroxide ions, each with a negative charge, separate from the barium. So we have two hydroxides that go off from the barium. So we write 2OH like this, and then aqueous. And so that should be a good equation to describe the dissociation of barium hydroxide into barium and hydroxide ions. Let's do the next one. Okay, so the next compound is copper nitrate. Okay, so copper nitrate is a solid, which you can add to water, and then what will happen is two nitrate ions will separate from the copper ions. So are you able to write this? So what I would write is Cu, and it looks like the charge of copper. Let's figure it out. We have, you may recall that copper can either be a +1 charge or a +2 charge. So we have to sort of figure that out. We have to indicate the correct charge here. So each nitrate has a single negative charge. We have two nitrates, so we have a total of -2 charge here. We have one copper ion in this formula. So to balance the -2 charges contributed by nitrate, copper must be +2. So it's copper 2+. And again, when it dissociates, it'll be surrounded by water. And so we indicate that with a state symbol of AQ. And then we write out two nitrate ions like this. And that should be a good equation for the dissociation of copper nitrate in water into copper and nitrate ions. Now, importantly, with the dissociation equations, what I did is I chose compounds, calcium fluoride, barium hydroxide, and copper nitrate that all dissolve well in water. If you can get a lot of mass of these compounds dissolved in water, it is said to be a very soluble compound. So that's important to note. So we will now move on.